The derivative of a function measures the change of the output value with respect to a change in its input value. Let's give an example. Here is a ball thrown upwards, its position changes with respect to time. The derivative of the position of the ball with respect to time is the object's velocity. This measures how quickly the position of the object changes when time advances. In the previous video about limits, there was a graph representing a ball being dropped. We wanted to know the speed of the ball at time 0.5, and we found out that the speed was 4.905 meters per second. We did this by making a secant line, and bringing the other point as close as possible to the blue point. To find the tangent at the blue point, we find the gradient of the secant line, and then bring delta t close to 0. We can represent the tangent line at blue point like this. This represents the derivative of s with respect to t. Suppose there is a graph that represents the function of x with respect to x. To find the gradient of the tangent at a particular point, you just have to find the derivative of the function of x with respect to x at that point. Since we use limits, it is said that dx represents instantaneous change in x and df of x represents instantaneous change in f of x. Whenever you hear the definition of derivatives, you will often hear that the derivative of y with respect to x is the instantaneous change of y with respect to x. There are two very common distinct notations used for representing the derivative of f of x with respect to x. One way is using df of x upon dx, and the other way is like this. This is read as f prime of x. Here is a graph of f of x is equal to x squared. Suppose we want to find the gradient at x is equal to 3. Like before, we would choose another point, and limit the distance between them to 0, let's call the distance between them h. As we know, the gradient of the line is change in y upon change in x, and we must limit h to 0 to find gradient when x equals 3. In our case, we know that x is 3, and since f of x is x squared, we can expand our expression. Over here we found out that the derivative of the function when x is 3 is equal to 6. Finding that answer took a bit of time. What if I told you that there is an easier way for finding the gradient at any point for this graph? Let's look at the formula from the beginning. We know that f of x is x squared, so we can expand that. After that we can remove the x square, and then cancel out the h. Since h is approaching 0, we can remove the remaining h. Now we are left with 2x. So in other words, we can say that at any point of x, the gradient will always be 2 times x, so that means when x is 2, the gradient at that point is 4, when x is 1, the gradient at that point is 2, and when x is 6 the gradient at that point is 12. The process of finding a derivative is called differentiation. When we differentiated x squared with respect to x, we got 2 times x, but how do we find the differentiation for exponent other than 2? Firstly, let's say function of x is equal to x to the power of b. We know that derivative of the function of x with respect to x is equal to instantaneous change in function of x divided by instantaneous change in x when delta x approaches 0. Now let's put x to the power of b in place of f of x. Before going any further, we need to expand x plus delta x to the power of b. When you expand it, it will look something like this. To know how to do expansion like these, you can watch the video I made about binomial expansions. Anyways, take a closer look at the second term, because this is going to come important later. Now let's put the expansion into our equation. This may look a little complicated, but it's not that difficult to simplify. First we remove the x to the power of b, then we get this. We know that all the terms have the value of delta x in it, for we can factor out delta x from the numerator, and then cancel it out from the denominator. As you can see, this is what we end up with. In this equation, all the terms except for the first one, has delta x in it. Since delta x approaches 0, all the terms will end up being multiplied with the 0, and the only term that will remain is b times x to the power of b minus 1. So it is safe to say that when we differentiate x to the power of b, we get b times x to the power of b minus 1. The differentiation of x cubed is 3x to the power of 2, the differentiation of x to the power of 4 is 4x to the power of 3, and the differentiation of x squared would be 2x. We can also say that the derivative of just x is 1. We know from the properties of limits, that if a function is multiplied by a constant, then when using limits, the constant can be taken out. Suppose g of x is equal to k times f of x. Since the derivative of g of x is instantaneous change in y upon instantaneous change in x while limiting delta x to 0, since g of x is k times f of x, we can substitute f of x inside the equation. We can also take the common factor out. Using the properties of limits, we know that constants can be taken out. From this, we can say that the derivative of g of x is equal to k times the derivative of f of x. So now if we differentiate something like 5x squared, we get 10x, if we differentiate 2x cubed, we get 6x squared, and if we differentiate 4x, we get just 4. If in case you have an equation which is just y equal to some constant c, then dy by dx will be 0, this is because you can think of the equation as y is equal to c times x to the power of 0, after using differentiation, the constant c will end up being multiplied by a 0, so that means that dy by dx will also end up as 0. Now, let's try solving a problem using differentiation. Here we have a graph of 4x to the power of half. We need to know what the gradient is when x is 4 and when x is 3.5. Since y is 4x to the power of 0.5, then dy by dx is 2x to the power of minus 0.5, so we can say when x is 4, the gradient is 1, and when x is 3.5, gradient is 1.07. Suppose there is a function of x which is the sum of two different functions. We already know what the equation for the derivative of f of x is. If we put g of x and h of x into the equation we get this. Now let's put the like functions together. After we have done that, we can now split both of them, so we get this. We also know that since delta x in both fractions is approaching 0, so then we can write this equation like this. Now we proven that derivative of f of x is equal to the derivative of g of x plus the derivative of h of x. So for example, if we have something like f of x is equal to x squared plus 4x, then the derivative of it will be 2x plus 4. Now let's try to solve a problem using this property. Suppose there is a graph with the equation 2x squared plus x cubed. We need to know at what x value is the gradient equal to 0.5, since y is equal to 2x squared plus x cubed. Then dy by dx is equal to 4x plus 3x squared. Now all we have to do is equate the gradient to 0.5, and then find the correct x value. Using simple algebra, we find that x is equal to 0.115 and minus 1.45, so this means that when x is minus 1.45 and 0.115, the gradient of the graph line is exactly half. Before ending this video, I would like to talk about second-order derivatives. When we have a graph and we want to find the gradient at a certain point, we are only asking what the instantaneous change in y value is in very small changes of x. For example, if we want to find the gradient of this line, at this x value, we would just try to use dy over dx. This basically means change in y over very small changes in x. Similarly, second-order derivatives is basically double differentiation, and it means the change in gradient at very small changes in x, and it is usually written like this, or this. As an example, let's use the same graph we worked with before, and let's try to find the change in gradient when x is minus 1. We know that dy by dx is equal to 4x plus 3x squared, so if we differentiate that, then we get 4 plus 6x. When we substitute minus 1, then we get minus 2. Now suppose we have two variables, displacement and time. When we differentiate displacement with respect to time, we get velocity, and when we differentiate velocity with respect to time, we get acceleration. We can go even further and differentiate acceleration, to get jerk. We can even differentiate jerk, to get jounce. Thank you for watching. I hope you understood the topic very well. Please like and subscribe for more videos.